Okay. Well, I think my diary should be fine now. 2 hours should be enough. Yep.
Okay, so we are now going to have our 2 proposals for follow-on research to students. The first one is by Mark Zikos.
Okay, so I'm Marcus Dreyer, and I'm going to talk about bilingual parsing and language models. So someone asked for examples of our translations. Well, here's a non-fluent translation as an example to introduce and motivate my research. So it's, on the other hand, source added verse 7th, 1926. It's translated from some Arabic sentence. I don't even show the Arabic sentence. Because the point that I want to make is we can get a little more fluent if we integrate a target language model. And I'm going to show you a second sentence, which is still bad, but it's a little bit more fluent. And here it is. On the other hand, source added a 7th, 1926. So where has been changed to a, and this second sentence actually comes from very basic experiments with the model that I'm proposing today. So it's getting a little bit more fluent. How do we do this? Well, we integrate more knowledge about the target language, right? So integrating a target language model with our system should help and make it know that added where 7th is not so good, added a 7th, if both hypotheses exist, should probably go up. And the great advantage of doing this is also we can train a separate language model on the vast amount of English data that's out there on the web. See the gigaword corpus, and that must help. And we'll see that it does. I have some basic results. So what I'm proposing is to conjoin 2 models, the biparser, the bilingual parser, and a target language model for English in our case. So there has been previous work, and I'm going to propose several advances over past approaches. So there are several possibilities to do this. You could do a post-processing. So that's what actually Yamada and Knight did. So they had their translation system in place. They got n-best translations, and after that, as a post-processing step, they re-ranked those trees according to a language model using a trigram-based re-ranking algorithm. Well, the downside of this is, of course, you lose good candidates, right? The ones that fall below the n-best translations might also be good candidates. It's also inefficient, right? So we can do, of course, better, and we can integrate the 2 models more closely. So we can re-rank at the sub-hypothesis level. This has been proposed before. It's more elegant methods to do this. And yeah, so let me talk about this idea of conjoining 2 weighted deduction systems, the biparser and the language model. And let me talk about this idea, re-ranking at the sub-hypothesis level. And let me show several variations on this topic and some very first basic results. Okay, so let's think about the derivation process as driven by the bilingual parser. So the derivation process goes according to the bilingual grammar, and we mix both scores of both models. So for every sub-hypothesis that the bilingual parser makes, proposes, it assigns a certain score, right? It assigns the inside score, and we can at this point mix in the score given by the target language model, get a mixed score, and then put the item on the chart and go from there. Let me give you an example. So, and it's in German. So after 6 weeks of workshop, it's hard to imagine. There's not only French, Arabic, but we always have Russian. No, we have German. Okay. A simple sentence: Ich sehe dich, I see you, and we have bilingual items in our parser, right? The German side and the English side is empty for this. In the scan, after the scan process, we get the corresponding English items from the load component, and of course all of the items have a score assigned by the grammar. And now our target language model comes in place, and we can here assign unigram probabilities, right, to those words on the target language side. I see you. And now the derivation process.
The reason you have C is because you have it in the dictionary for there.
Yes.
Yes.
Yeah.
Okay.
So there is a load component that loads the some corresponding words onto the chart. And then we can combine according to the bilingual grammar. So we combine those to a two-dimensional item, and still this covers just the word I on the left side, right? And we still have the probability of I here for the language model. And also we have the grammar score. And so it goes. And now it gets more interesting. Now we can combine C and U, right, to a VP. And the grammar assigns an inside score. And the if we use unigrams, we have this probability. But now U has, so U gets the left context now. So it's CU, so we can use the bigram probability in this case. So divide out the unigram probability, multiply in the bigram probability. And the derivation process continues, and in the end we arrive at the sentence level. So again, for the target language model, we multiply the two item scores together, and again, now C has a left context, so use the bigram probability. And now it's done. So we had the goal, and we can multiply in this score. Okay, so the derivation is driven by the bilingual parser. We mix the scores, and we can, of course, mix the scores in different ways. So we can use a mixture of experts. We can use a products of experts. So we can have these different methods of mixing, and we can, in the experiments that I'm going to show you, I just did a uniform mixture, and we can of course we can make a weighted version, and we can also have the lambdas be a function of the constituent type. So for a NPV, for a base noun phrase, maybe the target language model might not be so important because it's short. For a VP that consists of several constituents, it might be very good, and training and the parameter optimization might show that the target language is much more important here. And there are more things to do and to try that I'd like to propose. So instead of starting out with the unigram probabilities, we can use optimistic bounds and use bigram probabilities from the beginning. So instead of having the probability of U here, the plain one, we just take the highest bigram probability possible. So it's an optimistic bound. We take, let's say it is U given do, for example, and then the same derivation process continues, and we have used optimistic bounds here related to A-star search. Okay.
So can you limit the potential conditioning words to those that are within the set that have been loaded?
That's a very good idea. Yes, yes. We could also, that brings me to this point, we could also limit the Ngram model to only the words that were in the training corpus, in the parallel training corpus, which would be a very good extension, which I didn't do in the experiments, right?
So the do is selected as being the word for which U is the most probable that U can be.
Right, right.
Yeah, and what's the motivation again?
So it's an optimistic bound, and it's
Not the bound.
yeah,
It's for A-star parsing, is what it is.
yeah. So it's a one-step look ahead. Right. So we can use optimistic bounds. We can also see what the effect on search is on pruning. So it might turn out that the relative gains that we get are greater with more aggressive pruning. So it's interesting to look at the effect on search. And since the non-fluent item are pushed below in the priority agenda, so we get faster Viterbi decoding, and the model is more resistant against heavy pruning. So there are more things that can be done and that I like to do. So we could use more knowledge sources than just the two scores, the grammar score and the target language model score. We could use a length penalty of the translation component as compared to the input component of each constituent. We could use more sophisticated target language models. So this is so what I've shown you is just the most basic, simple example, of course, of a bigram model. So of course we can use trigram models. We can use more features in the target language model. We can use spelling features. We can use class-based models and basically take advantage of developments in the language model literature. And we can also train the Ngram model specifically for this task, right? We don't have to take an off-the-shelf Ngram model that's also used for speech recognition or other tasks. We can train it specifically for this task using contrastive estimation. So take a reference translation and take several other bad translations as a neighborhood and train. Okay, so that's several extensions and variations that I'd like to look into. And now I'm going to show you a very basic experiment with basic settings. So just take a bigram unigram model, and it's trained on 10, 15, and 20 million words from the gigaword corpus, and on the one side, and then use a bilingual grammar. It's trained only on 10,000 sentence pairs, so the results are basic. And what I did with the scores is just multiply the scores incrementally. So there's no sophisticated weighting here. But the scores are really good. The scores I got are nice. So let's look at the left group here. The pattern is the same. So I did no pruning. I got the one on the left is without any integration of bigrams of the Ngram model. And it's 0.1735. And then it goes way up when I plug in the target language model. So that's nice. And I have different results.
What is the blue score, or what is it?
Oh, sorry. So it's here. It's the GTM1 score, and that is the first score that Dan explained.
And the translation is obtained by.
Yeah. So I did these experiments in our system, in the GenPar system, and it's Arabic to English, so trained on 10,000 Arabic English sentence pairs. GTM1 score, where you count the matches and take the harmonic mean between precision and recall.
The words are correct, sort of in the best forms. Yes, yeah.
front setback.
That's what it means.
And did you, when you integrated your language model, did you do this as you were suggesting within the chart, so on the sub
Yes.
level all the way up?
Yes, so for each constituent, right, the score gets mixed in all the way up, right.
Did you need to change the bilexical grammar to make it into a conditional probability rather than a joint probability model?
No, I didn't do that. So we still use the joint probabilities,
I see.
and the bigram scores are mixed in.
So to say that, if that's the case, to say that there was no language model before you put this in
Okay.
isn't quite accurate, right? Because implicitly there's a syntactic
Yeah.
language model in what the rest of the team has been doing already.
Yeah, right.
You
So,
just want to multiply in effect another feature.
Right.
Which is bigram score.
okay.
Is that right?
Yes, I mean, I would see it as a combination of the two models, as a clever combination of the two models, and but it's true that the bilingual parser, of course, has knowledge about the target language, and I mix in a second source of knowledge, basically.
So to understand the pruning, this is done on for any given cell. We're trying to figure out which.
Yeah.
I'm
So.
worried about comparability. I mean, as you get longer and longer strings, the n-gram probabilities, you'll take a larger and larger hit. So you need to be able to guarantee some comparability among candidates.
Okay. So the pruning is a simple beam search, and
But am I comparing cells of different spans?
it compares. Yes, I mean, it's the same beam search as in every monolingual parser, right? So for each span, if it's smaller, if its score is smaller than a certain fraction of the best item
For that span.
right,
Okay.
right, it gets pruned.
But I think that Brian's point is still valid because as these spans get bigger, the language model scores just go down.
The same
And
is
if
true
it-
for the
Right.
bigram.
I'm sorry?
The same is true for the bigram score.
Yeah.
The language model score.
So they're still comparable.
Oh, I see, okay. As long as they're still comparable.
Right, yeah. Okay, so these numbers are good, and I'm going to show you some more graphs that also look good. So for the GTM2 score, we have a nice result as well. I mean, the target language models gave a nice result. On the left, you always see our baseline system, and it goes up when I plug in the target language model. So we have this, so the highest value here is 0.2337, and I point this out here because, again, this morning we got new numbers from Andrea this time, and she trained a off-the-shelf system with Giza++ and the CMU toolkit, and on the same data set that I was using here, the 10,000 sentences, and she got, so the value she got for this score, this is GTM1, was 0.2310. So, I mean, take these numbers with a grain of salt because she took it off the shelf and didn't play around with parameters. And it's small training data, but it's a promising first result. Okay. And we have GTM2 scores here for Arabic and English as well. Yeah, that's the second graph. Okay. Yeah. And now these numbers can also be compared to the CMU toolkit numbers where Andrea got 0.1024 and I have here 1008. Okay.
Testing data is 2003.
Oh, the testing. The testing can you, so I test on 100 sentences.
Types 2003 data.
Yeah, on the test sets that Dan mentioned before. And now French to English. Here I just have the heavy pruning results. The others are still running. And it also goes up. That's the message of this slide. Okay.
What's the effect actually of the pruning here? Actually, that was interesting. I think on the first slide
Yeah.
you had all three conditions.
Right. On those slides I had the three ones. I mean, they're basically very comparable. They're basically the same, right? I don't know if...
The point about this, to some extent, is that you would hope that this extra information would provide you more discriminative scores across the items that you have in your cells, so the
Right.
pruning would be more effective.
And there's some suggestion that that's going on, right? Because the difference, the effect of having a larger model looks bigger when you're doing more heavy pruning.
Right.
I mean, there's no measurements of statistical significance here, right? This is all very
Right.
preliminary, but
Yeah, so I'm not sure if I can make a point about these differences because I didn't do significance tests. I mean, the difference between the basic model and the biogram models integration looks significant, and I don't want to say too much about the differences between these. Right. But I like to look into this.
Question.
Okay.
100 standards is only in the test set, right? You said you took which 100? The first 100, the shortest 100, and what?
Oh no, it's the first 100 sentences. Okay, so with these experiments I'd like to conclude my talk. So I suggested to integrate a target language model and a bilingual parser and guide the biparser toward more fluent translations. And I've shown some advances and variations, what can be done in this framework. Use better language models, use optimistic bounds that relate to A-star search. Use different mixtures, use more experts, train the Anger model specifically for this task. And I've shown you baseline results that really look good. And so I'm looking forward to do this research. Thanks.
questions for reporters?
Okay.
I was just wondering, do you think there's any way of actually using external data just to improve the one side of the bitext grammar?
Yes, that would be possible.
I mean, there ought to be an EM algorithm for doing that, for example, but
Yes, that could be done too. It might again improve the numbers. Okay.
Okay, there's going to be time for more questions later.
Thanks.
Did you get that spouse with it?
Yes, you do. So, just want to echo what Marcus said, right? This is very preliminary, right? We didn't do any statistical significance testing, but I'm very encouraged by the fact that our first cut is sort of in the same ballpark in terms of accuracy as an off-the-shelf system of the other kind, on which people have been working for 10 years.
Dan, can you just say something about the, so one of the students used the GSL to train the translation model. Is that word translation?
Yes, it was just word-to-word. Right? Again, we're going to plug in phrases too, but we haven't yet, so that's probably better comparison. I also wanted to say, this particular topic is that I'm personally very pleased with it because there's sort of a myth out there that if you're doing translation by parsing, then somehow that's incompatible with having a target language model. This demonstrates that this is completely false, right? You can plug in a language model here just like you do for a noisy channel. So now we will have our second student proposal from Ben Wellington.
Still. Okay.
Having some technical difficulties. So my proposal is that we change the resolution. 640 by 480 at 90 hertz. It's much more effective than some other. And we're actually putting in a forest in the quad to make the campus more beautiful. Yeah, it's a parse forest. Yeah. Yeah, of multi-trees. You can see. Those trees are actually multiple dimensions. If you go outside, you can actually see them. They're not one-dimensional trees. You can walk around them. So they're actually three-dimensional. Yeah. We saw them pruning actually 2 days ago. So they put out the tape and everything. You had to go around. So anyway. All right, that wasn't actually my talk. If you were confused, some of you might have been. So I'm going to hopefully help you out here. So the title of my talk is actually looks similar to our title of the workshop, but it's Statistical Machine Translation Evaluation by Parsing. And I want to emphasize that the statistical is modifying the evaluation and not the machine translation. So this is evaluation for all sorts of machine translation that's statistical, as opposed to only being able to evaluate statistical machine translation. Just wanted to put that out in the beginning, so it's not confusing. So I think we're all familiar with some of the approaches for evaluating machine translation. There's a lot of n-gram-based approaches. There's BLEU, NIST, and GTM, which is what Dan was just discussing, which is the F measure, one version of the F measure. And so I want to discuss some of the shortcomings of those approaches. I think this is not new. People have pointed these out for quite a while. So here's a sentence. We have a reference and 2 candidate translations. The reference reads, "The president frequently makes his vacation in Crawford, Texas." And we have 2 systems, and they both come up with translations. The first system came out with, "George Bush often takes a holiday in Crawford, Texas." And the second system comes out with, "Holiday often Bush takes George in Crawford, Texas." Now, of course, using these n-gram approaches, whether it be BLEU, NIST, or GTM, it'll score these 2 translations exactly the same. And I don't know, I don't think that's a good thing overall. If you want to be building better systems, you want to be able to distinguish between these examples for obvious reasons. So maybe we need to incorporate some sort of syntax. What was the difference between those 2 sentences? Well, one was grammatical, and one was, as Dan calls it, word salad. And we want to be able to tell the difference between those. And n-grams is just not going to cut it here. It does help in some situations, but not all. So let's possibly incorporate some syntax here. And how are we going to do that? Well, we saw a talk on translation error rate, which I think moves slightly in that direction. And some people propose the idea of, let's see if the output sentence is grammatical. And that can help us to see if our evaluation is good. So here we are. How would you do that? How do you see it? How do you know if a sentence, an English sentence, is grammatical? Well, I mean, it's not too hard to think of a way. You take your sentence and you put in a parser. The parser, let's say, has no smoothing. We disable all smoothing here, and it's just straightforward, some sort of PCFG. We put in our parser, and out pops a tree. That means it's grammatical, right? Of course. And if we put this other sentence, "Holiday often Bush takes George in Crawford, Texas," we get the big it means it's not grammatical. So you can actually tell the difference between a grammatical sentence and an ungrammatical sentence just using a simple parser in one language. So alternatively, you can maybe get scores out a lot of parsers will put out a tree anyway. So we have this number here, and it's telling us, all right, this tree here is more grammatical than, this sentence, is more grammatical than this one. So I think it's a step in the right direction. In this case, we basically can probably mix that with we basically have even n-gram matching scores, and one has a higher grammatical score. So let's choose T1, and in this case, that actually works. So, all right, we've gone another case down, and we're moving in the right direction. But I don't think, and this has been proposed, but we're not there yet. We're still missing something very fundamental. So let's say we have this random sentence, I think was from some corpus somewhere. It's Fred asked Sanjeev on Friday about that odd student from NYU. We have 2 translations possible. We have, on Friday, Fred asked Sanjeev about that odd student from NYU, or Fred from NYU asked Sanjeev on Friday about that odd student. So I ran it through these 3 measures, and they all prefer the latter. These are both, let's point out that these are both grammatical sentences. It's unclear if you were to stick them into some English parser whether you'd get even scores out. You'd probably get very similar scores. There's no way to know which of these, just by, if we cover up this reference and knock it out, and I were to hand you these 2 sentences and ask you to tell me which is a better translation, you'd have no idea, and either could a English parser, for example. So what are we missing? Well, we realize that Fred is not, in fact, from NYU, but from Johns Hopkins in this corpus. Just want to point that out. The idea is that we're taking meaning here. So it's not just it's not just, is it grammatical? It's, does it have the same meaning? So there's two things we're capturing at the same time, the same meaning and grammatical. So how do we go in that direction? Well, as I said, it would be nice to incorporate syntax. We've looked at that. Let's take it a step further. It would be nice to incorporate synchronous syntax into our evaluation metrics. So how do we go about that? Well, let's assume for a second we have that we have a transduction grammar of English to English translations. So it comes from above. We don't know where this grammar came from for now. We'll put that aside. We got this great grammar that basically encodes all of these different paraphrases and different basically meaning-preserving syntactic alternations. I'll give you some examples of those in a second. But let's just say we have this transduction grammar. So why not take our grammar and try to parse two input sentences, the reference and the candidate, into our bigrammar. And if it comes out with a tree, we say, okay, it's an acceptable translation. Or the other option, of course, is if we want to score, we take the score of the biparse, and we treat that as some sort of metric of how good the translation is. And this actually takes into account two things. Is it grammatical? Because if it's not, it won't work. And if it's not a good translation, it won't be able to do a biparse either. The scores will be much lower in the case where there are different translations, or much lower in the case where your output is in the wrong order or is word salad. So, of course, this is assuming that you have a grammar. And they're not lying around. So how do you go about getting one? Well, you could have experts produce a grammar. We like to call these experts who do things for us. So we have experts who come forward and could create maybe some sort of grammar that basically has syntactic alternations encoded. So an example is, here's two noun phrases. So if you say like the flight from New York to Dallas versus the flight from Dallas to New York. So these things have the same meaning. So we should be able to capture that in the grammar. So in this case, you stick two different basically production rules into your grammar. One which keeps the order and one which reverses them. This is kind of unrealistic because who's going to sit around coming up with every single one of these possibilities? I don't think it's going to, it's very expensive and it's probably going to have pretty low coverage. So usually when that happens, people come up with this other idea. You have students try it, and it's less expensive, but it often has lower coverage. So that's probably not the best approach, although it has been used. So we're going to try to basically get a transduction grammar automatically and induce it using GenPar. So basically, we're going to take multiple translations corpus and use it to train our grammar. And hopefully, if it's trained right, then we'll actually be able to encode synonyms and paraphrases and some other interesting syntactically equivalent alternations, such as from France to Italy from France, or give the book to him versus give him the book, these kind of things. And if you do this right, you're going to be able to encode this in your grammar productions. So how do we build this corpus? Well, we take these corpora that have multiple translations. So here's some sort of reference. You have 4 references for some French translation, and there's 4 English translations for it. So we're going to take these 4 English translations, and we're going to align each one with itself and all the others. So in this example, we're basically taking these 4 sentences and making 16 sentence pairs, where you match each with one of the other ones. And what you're doing is you're actually getting translations, right? This is a translation of this. This is a translation of this. And if you build your grammar right, you're actually going to capture these interesting grammatical alternations.
Could you just explain to me again where are these reference texts coming from?
Well, there's a lot of the time when you're doing, I guess, evaluation, they have multiple references. So they've actually produced some. The LDC has actually produced some.
So you're going to take the evaluation from other ends.
Mm-hmm. Okay. And so we've tried this, so I have a little bit about it, but I'll get to that in a second. So we take these. Now we have this big corpus of English to English translations. Or basically, I want to call it paraphrases instead of translations. Probably a better word for it. And we're gonna use some sort of grammar and an English parser, and using GenPar, build some sort of transduction grammar. So of course, the better this grammar becomes, the better this is going to work. And so it's dependent on how well your grammar formalism is working and things like that. So with this solution in mind, you basically can say, all right, take this grammar and score your sentence pairs. And that score is your evaluation of the translation. And that's it. So that's one proposed solution. And it is kind of hairy because there's a lot going on, and it's not going to automatically tell you how great the translation is. And your grammar is not going to be perfect, and there's a lot of issues there. So there's another possibility, and I just want to do a quick review. As Dan discussed, this is the F measure as implemented by GTM. And the idea is we're going to look at basically, in F measure, we're going to look at the exponent 2. So exponent 1, as we said in the scores here, is the unigram match. And exponent 2 is this measure of X measure. So in this case, F measure, excuse me. In this case, you have this grid. George Bush often takes a holiday in Crawford, Texas, and the president frequently makes his vacation in Crawford, Texas. And we have a 3x3 grid that we filled up by taking these unigrams, and since they're adjacent, this is just n-grams. This has nothing to do with parsing for a second. So we have this 3x3 grid, and your value is going to be 9 out of 81 is going to be your score, because the biggest possible F measure you could have if you cover the entire thing and every word is aligned would be 81 little boxes, and we filled 9 of them. So there's your score with the exponent 2 for F measure. Now, of course, when you mix it up, holiday, often, Bush, A takes, George, and Crawford, Texas, we already pointed this out. You get the same score with GTM, with blue, with NIST. So we're looking into basically extending this idea of coverage. So in GTM, you're looking for n-gram matches. So we propose basically using parse coverage in the same manner. So I'm going to explain what I mean by that. So here, let's say your parser is able to create a couple of basically partial parses bottom up. So we start with these words and we build bottom up, and we're able to actually make just a little tree that says in Crawford, Texas, aligned with in Crawford, Texas. And so that's it's basically got 3 words in English and 3 words in the target and 3 words in the reference. And so you can look at it as a 3x3 tree. I'm just going to use that terminology. And so you got a score, you basically fill in this box. And similarly, you're able to align makes his vacation with takes a holiday, and maybe the whole sentence maybe can't align because it's not perfect, but you get these sub parses, and you're able to get sort of you basically add up these scores and you calculate F measure the same way. What percent of this grid is filled in? So in this case, it would be 23 out of 81. And this is not a real example. This is just something I'm throwing out here. And you could alternatively, you could actually weight them, come up with some weighting scheme. I haven't thought in detail about this, but basically take your parse score and try to integrate it into this matching. It's a rough idea. And of course, if you mix it up, you're going to get a lower score because you're not going to be able to create bigger parses. Your parses will all be scattered. You might have a parse that contains a single word and a single word, but you won't be able to create larger parses. So you'll get a lower score, and you can actually tell the difference between these two examples, which is important. So here's an example of what something that we induced using GenPar, and it's actually a part of a sentence. We didn't filter for sentence lengths, and so most of these sentences just go on a long way, and so you're already having trouble seeing it, so I just took the upper left corner. But the sentence is, the CIA has always been skeptical about the claim that, and it's the U.S. Central Intelligence Agency is always suspicious on. So obviously using an n-gram here is going to be troublesome. How are you going to know that CIA is Central Intelligence Agency? Well, with an n-gram matching, you don't. That's just thrown away. But we've actually captured in this grammar automatically using GenPar. We've captured bottom up, basically based on some constraints that it's guessing that CIA and Central Intelligence Agency go together, based on the fact that on the ordering information and other things. How that's done exactly is beyond the scope of this particular talk. But so you can see that we've captured the paraphrase, and so this is the idea. If we can use this during evaluation, we should get better results. So we already have GenPar. We can already do parsing. Why is this interesting? Why is it just a matter of running experiments? What more is there to do here? Because we have the toolkit, and I'm proposing that you can just parse, and that's it. And the answer is that we've run some basically preliminary experiments, and we ran into some barriers which I want to show you, which I want to explain to you and propose solutions. So I think first of all, there's a limit to we're doing basically bottom-up constituent-based parsing. So I'm going to show you how that would work. We have 2 sentences, Ben loves sunny Baltimore, and Ben loves Baltimore. So if we're going bottom-up, we can start to basically parse from the bottom. So we align Ben, and we align loves, and we move up, and Baltimore. and we're stuck there. So we basically have 3 partial subtrees, and we're not able to attach them any higher because of the differences in the structure here. And so we're left with 3 basically 1-by-1 trees, I'm going to call them. One that contains the Ben. These are actually attached in a multi-tree. So you have a tree that contains Ben and Ben, Loves and Loves, and Baltimore and Baltimore. And if you were to measure in this F measure style, you'd get a 3 out of 12 score. Now, let's say instead of Ben loves sunny Baltimore, we get the completely absurd statement, Ben loves leaving Baltimore. So that's a different meaning. It's absurd. And it's basically, you want to be able to capture the difference between these 2 statements, right? Because I think Ben loves sunny Baltimore is a much better translation than of Ben loves Baltimore than Ben loves leaving Baltimore is. Why? Because in both the first examples, Ben loves sunny Baltimore and Ben loves Baltimore, the important part is that I love Baltimore, no matter how you slice it. When you add leaving here, you're basically, I love leaving. And that's a different statement altogether. And once again, n-grams aren't going to capture this. And it turns out, unfortunately, that bottom-up parsing is not going to capture it either. Why? Because we're stuck. Again, just like we were before, there's no match for leaving, and we're moving bottom-up. And we can't parse any better than this, so we end up with 3 1-by-1 parses again. We end up with the same score. And unfortunately, this technique is not going to capture the difference between these 2 translations. So I think it has to do with the fact that these are bottom-up. And I have 2 hypotheses to try to solve that. One is to try implementing an synchronous early algorithm or some sort of top-down algorithm. I'm not sure precisely which. But if you go top-down, you see you can actually capture Ben loves Baltimore. And basically sunny is this adjective here that's not included. Yeah, you have a question? Okay. Sunny is this adjective that's not included here. And we end up with basically a 3-by-3 parse, in essence. And so your score is going to be 9 out of 12. Because, yeah.
What happens if Ben hates Baltimore is the alternative? The parse look the same.
Okay, well, if your grammar encodes that hates and loves can go together, then you would be able to align. But if your grammar has that, which it would be unfortunate. Not to say that doesn't happen. It could happen, yes, that would be a problem and it would cause an error. But I would hope that hates and loves would not be encoded as basically in the grammar as being able to align.
As paraphrases.
Yeah, as paraphrases. So, but yeah, it would be the same kind of parse.
So you're right, I did have a question before.
Yeah. Go ahead.
Is this really a question of bottom-up versus top-down parsing, or is it a question of how you assemble fragments? I mean, it seems like you want to change the model, whereas what you've described is changing the algorithm. Now you may need to change the algorithm to change the model.
So that's my next slide.
Well, then go on to the next slide.
But that is a very good point. It's genius. It's so genius that it's in my talk. So that's good. No, I'm just kidding. No, it's a good point. We're gonna get to that in a second. So it's the alternate hypothesis, basically. So the one hypothesis is that top-down parsing will help in here. Like I said, there's a 3-by-3 parse. So your F measure score is 9 out of 12. If you change it to Ben loves leaving Baltimore, what happens? Well, your top-down parse gets stuck, and you have this 2-by-2 tree. But what you can actually do is you can get more information than just this, right? Because you have a chart, and your chart's full of partial parses. So you can actually, just like in GTM, you do this maximum matching. You can do some sort of maximum weighted cover algorithm, and go to your chart and try to get out the highest scoring parse cover that you can possibly have. So we might go and find another sentence in your chart that basically covers Baltimore. So you end up with a 1-by-1 and a 2-by-2. So that score is 5 out of 12, and that's lower than with the Ben loves sunny Baltimore. So you're actually able to distinguish because of the actual meaning. We're capturing meaning here that these are different, and that's important for evaluation. So another possibility is to change the grammar and the actual model you're using. So in this case, here's dependencies. And if you go bottom up sort of with dependencies, you could say, all right, we could get these subtrees here. And once again, we have a 3-by-3 parse bottom up. So we were able to align Ben loves in Baltimore, and we're capturing some meaning here. And if we change it to leaving, well, we end up with a 2-by-2 with Ben loves and a 1-by-1. So once again, we're distinguishing, based on these dependencies, we're distinguishing what the meaning is. And so that's actually a change in the grammar. Does that address your question or no?
Sort of.
Okay.
I still don't understand in the context-free model why the parse algorithm is what's an issue.
It's just one idea to help it. You can change grammar form, you can add phrases, you can do interesting things to grammars. It's just one way to go about it. All right. So, and to throw into the mix here, you could also, for evaluation purposes, you create some sort of weighting scheme so that the higher towards the top of these trees you are in the dependency, the more important. So I would argue that adjectives towards the bottom of dependency trees are less important to translation than items that are higher up, closer to the base. So conclusioning on those options is that, well, we have these two sentences, and a simple F measure or n-gram-based approach can't tell which translation is better. And as presented, this bottom-up constituent-based approach can't necessarily tell. It can tell some of these sentences apart, but there are simple cases like this one. This is a 4-word sentence that it has trouble with. And I think that using dependencies or some sort of top-down parsing can actually handle this better. And why do this in GenPar? Well, it's a working multi-parser. And so that you have this basic infrastructure is already in existence. So instead of having to go find some paraphrases, you can induce them using GenPar. And instead of finding some sort of multi-parser, you can use GenPar. And we actually have, so to run sort of, just to get these basically EDA and find, what is this idea viable and what's missing. And why do we care? Well, that's a good question. Should always answer that. We care because as machine translation systems are getting more sophisticated, and you need evaluation metrics that can keep up with them. And if you don't, I see it as sort of like an arms race, where you're quick to create a better translation system, and you want an evaluation metric that gets better. If you can't capture any syntax, you're not necessarily going to be able. And even while developing, if you're using a score that does not capture syntax at all, and your sentences are getting better syntactically, you're not going to always capture that. There are cases where you will, and there are cases where you won't. And I think that the cases where you won't are important. So the game plan here, as I like to call it, is to implement some sort of dependency grammar possibly, or a new parsing logic. And also to integrate, as Dan pointed out earlier, phrases I think would help in this regard as well. And to use a multi-translation corpora, which the LDC has, to train in basically paraphrase grammars, and to check the correlation of the evaluation techniques with human judges and see how it does overall. So in conclusion, I think the evaluation can be made much more effective using syntax in this regard, and that GenPar is really an ideal toolkit for this cause. And I think it would be very interesting, and I would look forward to implementing it by parsing. So that's it. Thank you.
I'm concerned that
that's not good.
I think it's a great proposal, but I think it also ignores one thing about NT evaluation, is that getting the semantics correct may be more important than fluency. And loving Baltimore and leaving Baltimore are semantically opposite. And if it caused you to,
I think this captures. I think this captures semantics. I guess I'm unsure what you mean.
Well, it seemed to me that, and so correct me, that if you were happy with parts of the tree, that you were going to up the score, and the fact that one word implied directly the opposite.
No, I think that was a misunderstanding. So let me show that one more time. So. All right. So basically, this is one word difference, and the point was that if I went bottom up, that that must be a problem. But if you go either top down or look at dependencies, that you can actually capture that this is the wrong meaning here. So
Maybe Tom's question is, what if you said, I love visiting Baltimore? Wouldn't that look just
I love
as bad?
what?
I love visiting Baltimore. Wouldn't that look just as bad under your proposal as I love leaving Baltimore?
I guess it could, yeah. Unless the grammar somehow captured it. So that's,
relationship between love and visiting is
I think the high-level issue here is that, the reason why people are going towards syntax is because we're hoping that it's more closely related to semantics.
Right.
But I think an issue here is, do you want to build an evaluation system around syntax on the assumption that it's more closely related to semantics, when in fact, that's actually the thing that we really want to be evaluating.
Right, so...
Does syntax, does working with these trees, put it this way, I've got a little surprise, I would have a little surprise if we did a tree-based evaluation of MT, if tree-based systems didn't come out looking better.
But not just looking better, but what about correlating more closely with human judges? I mean, that's what's at issue.
But I think that's the thing. That's the thing you really need to show, right? I mean, because that's in a sense.
Yeah. So actually,
high-level question, right?
So I mean, there's different ways to there's the meta eval, right? There's the evaluation of your evaluation technique, and we'll stay away from meta eval because that gets hairy. But so I guess our proposal there's some common evaluation techniques. One is people use sort of Spearman and Pearson coefficients, and you take the human rankings and you put them against your system's rankings, and you calculate a score that way. And we're looking at a different proposal where basically you collect all sentence pairs that were judged by the same judge. So a lot of these things are averaged over different judges, and they get kind of hairy because you have some judges doing one system, some another, and the rankings start to get a little fuzzy. So we actually want to normalize for that and take every sentence that's scored by the same judge, and you compare two sentences. And basically that judge will say this one's better or this one's better. And we want to compare that to whether our system says this one's better or this one's better. And you do that point, you actually end up with a lot more data points than a Spearman coefficient, because if you're doing it sort of this binary decision, each one is a decision in itself. And so we think that would be a good way to evaluate our evaluation.
I mean, on the other hand, the only real information you've got is the ranking. I mean, you can you can extract all these binary decisions, but they're no longer independent. I mean, they're now.
No, it's not true. When a judge is given a sentence, they're not asked. I mean, they're asked to give it a score, right? Not to rate 5.
But if all the judge has really done is just simply rank these 5 sentences.
But that's not what they do, right? They're given sentences and they assign scores to them. So
but
that's different.
What I'm getting at is that there aren't 5 times 4 independent decisions being made there.
Yeah, that's true.
Right. So even though you may be extracting 5 times 4 binary results,
I don't know. I just think
there isn't that much.
I guess the idea is that there's less variance in each decision, so I just feel like it's more controlled. But I guess I see your point. Yeah.
My concern is about the learning of the bytext grammar that you plan with these existing paraphrase data, because the amount of paraphrase data that's actually available from MT-eval is not that much, because MT-evals are about 1,000, 2,000 sentences per year for about 1,000 per language pair. So 3-4 years, you're going to get maybe 5,000-6,000 sentence pairs, and the vocabulary in there is going to be limited. Do you really expect that the grammar, the bytext grammar that you're going to learn from this is going to be effective for what you're trying to do here?
So there's one proposal to that actually can counteract that, and that is it's a bit much, but let's say I'm running let's say I hold back some evaluation sentences and they're put aside for my own uses. So these are the ones that basically are going to be for a competition, right? You can actually take those right then and there and build a grammar off of, and you have coverage because.
Okay, the vocabulary is going to be the same.
Yeah. So you're set because your coverage is automatically on the domain of whatever this is, and you have the paraphrases of the sentences that you want to parse right there. So as long as you don't mix that with, as long as you don't let that out, you can have this thing waiting. And if you're running your own systems, you take your sentences you want to evaluate on, and you make a grammar. You don't look at it. You keep it here, and then when it comes time to evaluate, you use that. And I think that solves that issue.
No, it doesn't solve that issue because your translation system may produce translations that have words that didn't appear in any of these.
It'd still be valid paraphrase.
Exactly.
Right. Okay. There's still coverage issues, and I feel like it helps that issue. Would be a better way to say it. I'm sorry.
Particularly if you have to learn stuff like love leaving versus hate leaving. I mean, you're not going to do that from 1,000 sentences.
No. Well, you then can mix that with another grammar that has higher coverage. So I'm saying I'm not saying that it solves all problems. I mean, there's no such thing, right? But I think it would help. If it definitely help coverage, there's no question. And if you already have some grammar that's trained off a very big, well, the biggest you can find, obviously, some sort of corpus, and you mix that, and you basically add to that your evaluation sentences that you're going to evaluate on, I think there's information there that's useful. Now, yeah, it's not perfect, and there's going to be words that the translation system spits out that you can't recognize. But, I mean, I think that in general, if you can't recognize it, then Blue's not going to give it a score because it's not in your reference, right? So, I mean, yeah, go ahead.
I just want to mention also that it's probably easier to induce a transduction grammar when the two languages involved are in fact the same language, because you have this infinite size extra vocabulary where every word maps to itself.
Yeah. And I was actually going to suggest that maybe it might be worthwhile just, first of all, evaluating how well these sorts of grammars can be used just to make paraphrases. So
Yeah, I mean, I guess...
Maybe even sort of set that as a simpler subtask.
Yeah, that's an interesting task. I mean, I guess I showed... Agreed.
Paraphrase.
Agreed. I showed an example of something, but yeah, that in itself is an interesting question, and I mean, needs more looking into. I guess...
So that was done at the ACL workshop on paraphrasing last month. We actually had a paper on the Microsoft Paraphrase corpus using ITPs.
And so was this comparable with...
Yeah, it's a pretty reasonable approach to go. We didn't try to train it, but it was already doing something. And also a related problem of textual entailment, which is also monolingual and monolingual. So there's some very interesting results from the Pascal challenge on textual entailment, which is all...
And that's a very hard problem, right?
It's really tough.
Yeah. So unfortunately, I'd love to take more questions. If anyone wants to ask me questions afterwards, I'd love to stick around and answer them. But I think I used more than my 15 minutes, so I better hand over the floor to the next speaker. Thank you.
Okay, so now Takai Wu is going to tell us about an empirical study we did in the context of our work.
Oh, was this one? If you've got slides, do you have slides? If you have. All right, so is this thing? Okay. We've got, when I was talking with, I don't know, a bunch of you, actually, both from the workshop and from outside, I noticed two sort of frequently asked questions when I was trying to explain what it was that we were trying to do. And I guess mostly for the people from outside, the question was, what the heck is this ITG hypothesis? And the people who were inside the workshop were asking, how come there's no Arabic speakers on your team? And apropos of that, in particular for this set of experiments, I'd really deeply like to thank the Arabic team, especially Mona and Nizar and Khalil, and Owen and David for indulging all the questions that we had for them on this. The key question that we were trying to ask was, can Arabic-English alignments be covered with inversion translation grammar expressiveness? Why was this important? Well, because if not, then we'd have to expand to something toward syntax-directed translation grammar expressiveness, which is sort of the next step up. And like many of the recent tree-based SMT models, both our English, our Arabic and French baseline models actually fall within the ITG class. And so we want to know whether this is a valid modeling assumption that we're making. Right.
If not, then training and decoding could become much more expensive. So it seems like an assumption that's important to test before we invest too much time in building the model. Notice that traditional sort of transfer-based MT systems and also many modern EBMT systems generally in their rule formalisms implicitly or explicitly are allowing for SDTG expressiveness. And this gives them a lot of flexibility, which linguists love, but it comes at a computational cost. And the question also from a learning standpoint is whether it's too under constraint. What makes us really want to test this is that there's increasing amounts of comparative, experimental results under controlled conditions on other languages that have been supporting the ITG hypothesis more and more. But there's no results known at all for Arabic, or in fact, as far as we know, for any Semitic language. So this was sort of a key test for us. Okay, now I know that the guys in the workshop have heard this. For the people who are coming in from this fresh, I'll try to go through this relatively quickly, but so therefore please stop me if I'm skipping over something too quick. Just quickly to review what does fall within this ITG expressiveness thing. Here's an example ITG parse tree. It looks just like a context-free grammar kind of tree, but what's happening is that each of the terminal symbols is actually a biterminal, which generates token in English and a token, in this case, in Chinese, but we were working with Arabic. And for the English, it's exactly the standard order. The authority will be accountable to the financial secretary over here, right? Depth first, left to right. For the Chinese, you do the same thing, except that whenever you come to one of these inverted nodes, which you can tell by the bar here, instead of descending left to right, you're going to descend right to left. So that's where the inversion comes. It says this constituent comes in the inverse order, right? And so for the Chinese, for those of you who read it, it does make sense if you read out these Chinese words, 上菜城市, before you go over here to 负责.
So it's like a binary model.
Yeah, this one is binary. In general, in the inversion translation grammar, it doesn't have to be binary. But if it's not binary, you only allow two permutations, straight and inverted. In fact, I'll talk a little bit about that. But this is basically meant to be a quick review so you understand what it is we're testing, right? So the key thing that makes this work, this is another visualization of something that you saw earlier in Dan's talk also. The key thing that makes all of this work efficiently is that you can compose transduction hypotheses this way. And this corresponds to a straight composition. But if you think that these chunks align to each other, then you can compose in an inverted node. Right? And that very simple thing is what makes all of this stuff chug along efficiently for bilingual parsing, for translation, decoding, etc. Now, the thing about ITGs that's really nice, again, just a quick reminder, is that it really cuts down on the complexity of matchings compared to arbitrary permutations. So this is if you allow, 0 through 16 words or constituents to permute in any order, kind of like IBM models did. Any word can move to any position. And of course, this is n factorial over here, which grows very quickly. On the other hand, in comparison, ITGs, because of the way they combine, grow much more slowly once you get above this level over here, and this is the ratio. You can see it drops off quite rapidly. What's really interesting to look at is this kind of turning point that you've got here, where above this level, ITGs are just as expressive as permutations. Below this level, it starts falling dramatically, right? And so somehow right around here, 4 or 5, it's a very interesting point. And so here's that particular row. I've drawn all 24 possible permutations here and shown the 22 ITG trees that can generate those permutations. And there's only 2 that cannot be generated by ITGs, which are these 2, which are in fact the same case mirror imaged. So we can just look at one. And now if you think about this linguistically for a second, what this says is that you've got 2 words in the English, and for the translation, not only are you going to invert their order, but you're going to pull them outside both of the surrounding tokens over here, or constituents in general, right? Which is just a very weird kind of inside-out backward stretching. And what made us really sit up and pay notice to this class of expressiveness was the fact that going through huge amounts of parallel corpora 10 years ago, we notice this is a pattern that we just never ever see in the corpus. Whereas every other permutation you actually do see. Right. Okay, one last sort of just intuitive motivation. The ITG hypothesis says that is adequate flexibility, right? And here's an example of a quite messy kind of a translation that nevertheless can be expressed by an ITG tree. Right? So if you actually work through that tree, you will see that this tree generates this permutation. So you can get quite a bit of flexibility out of it. The rest of this is just showing you some more alternate notations and visualizations of using brackets instead of trees and so forth. What happens is the angle bracket here means inverted. Okay, so formally, again, quick review. The ITGs can be defined in this way. They're the equivalence class of syntax-directed transduction grammars. And those are Lewis and Stern's 1968, right? And Aho and Ullman 1969. So this goes way back. But there are three equivalent ways to define this, at least. There's actually more. Either you allow any length, they don't have to be binary productions or trays, but you only allow two of the permutations. Or you only allow binary rules, or you only allow ternary rules. Now, in this context, what I would like to point out is that context-free, you have to be careful. People sometimes get a little bit careless and start calling this context-free and so forth. The reason you have to be careful is because it's, context-free is a monolingual concept. It is defined in that world. It's actually turns out not to be precise enough or unambiguous enough in the bilingual case with transduction grammars. So specifically, if you look at the expressiveness hierarchy for transduction grammars instead of monolingual grammars, it looks something like this. We start off with the SDTGs, and then here, this is where it starts getting different from the monolingual case, because this is the rank of the productions, right? It's throughout this hierarchy, it's the case that SDTGs with maximum rank of k are strictly more expressive than SDTGs of rank k minus 1, right? And in the monolingual case, it doesn't matter what the rank is because you can always reduce it to Chomsky normal form. Now, there's a very interesting singular point once you get to 4, which is where the ITG stuff came from. It's the only point in this hierarchy where SDTG3 and SDTG2 are actually equivalent. And moreover, they're equivalent, as I mentioned earlier, to inversion translation grammars of any rank, right, where you just allow straight and inverted permutations. This ITG2 in particular looks kind of like a Chomsky normal form, except we're dealing with biterminals instead of monolingual terminals. The simple syntax-directed transduction grammar, that's just for completeness there. I'm going to skip the details there. But this one is kind of important. I'll talk a little bit about it. This is where you have an ITG, but you only have one undifferentiated non-terminal. Thanks. So I want to kind of focus on this area because in this area we find the most practical algorithms. They're polynomial time, and the constants and the exponents are still sort of within reason. As soon as you go above this, it starts getting really hairy, and you really don't want to run those algorithms. The bracketing ITGs here that I was talking about are the best for language-independent methods because they don't have any real syntactic categories in the non-terminals, whereas you probably want to move up here if you want to have categories of transductions in your non-terminals. So let's just to sort of give you an idea of what's happened over the last 10 years since we introduced the transduction grammar modeling approach for MT. A heck of a lot has happened primarily on the bracketing ITG side because they're easy to use, they're efficient, and they give quite good performance for a lot of things. There's also been some work using linguistic grammars. We've used actually some linguistic grammars in this class that had hundreds and hundreds of rules derived from grammars that linguists actually wrote. Like monolingual grammars, you can head transduction grammars. You can lexicalize them. and even more typically, you can do both. And so people have tried all sorts of variations of these with some really interesting results. Zhang and Gildea show a nice jump here at ACL. So this is just, again, a reminder. I'm not going to go through this. There's a lot of applications, given what I've just shown you for this, ranging from the original intent of grammar induction to help bootstrap bracketing when you didn't have a grammar on both sides of the parallel corpus, by-parsing, tree alignment, segmentation. This is actually very important. This is in effect what people today are calling phrase-based translation, because what you're doing is you're making no decisions about what collocations or what chunks or phrases to translate until you're optimizing the entire translation equation. And that, of course, is what gives you a big, big win when you translate entire collocations to entire collocations. Projection or coercion, transferring knowledge you might have on one side to the other via the shared tree structure, and so forth. Decoding, of course, in both cases where you have just a bracketing grammar as well as a linguistic grammar, early style, EM training, etc. And all of these things are efficient and possible because of that nice dynamic programming type of approach that you get from the restriction on the expressiveness that I showed right in the beginning. Okay. So the ITG hypothesis that we're testing for Arabic says that translation between any two natural languages ought to be accomplishable within ITG expressiveness. Right? That's what the hypothesis says. And we want to test that. It's obviously an extremely strong claim. Right? If it's true, then it has really major engineering implications because of the efficiency and so forth, and also scientific implications if you look at it from a cognitive standpoint. So I mentioned that we're getting more and more good, solid comparative results. So we're learning more about this. And specifically, people have been comparing against, of course, IBM models, but then also the later variations that have come on the tree-based SMT theme, like the ISI tree-to-string model and so forth. This is a sample of some of the interesting results. Word alignment coverage, Zenz and Nye showed that the bracketing ITGs give you better word alignment coverage than the IBM constraints. Similarity measures, the bracketing ITGs, you just heard about that, so I won't talk about that. That was Loish and al. Word alignment accuracy, Zhang and Gildea, compared against the ISI tree-to-string model, found significantly higher accuracy from using this unsupervised approach with bracketing ITGs. Decoding speed and accuracy for translation. This compared against the IBM model collaboration between ATR and Herman Nye's group, et cetera. Some of David Chang has this very nice paper at ACL, which is actually doing unsupervised induction of essentially an of highly lexical and phrasal ITG. We have some really nice results coming up next month on automatically extracting extremely parallel sentences from very non-parallel corpora. So let me just come back now to the hypothesis. Yeah, thanks. Well, I could stop now, or I could tell the punchline. So this was the question that we set out to test from the very first slide. Here are the results. We've got two measures of accuracy here, right? One is if you look across the entire corpus and you just look at all the word alignments, the alignments between words, and you count how many of them can be covered when you've byparsed each sentence pair.
Excuse me, and how did
then
you get the alignments? Oh no, you just run all. Okay.
Yeah.
So they are string-to-string alignments
so they're,
by the normal method.
Yeah. We follow Zenz and Nye's ACL03 methodology here. So you train up the best Giza models you can. And in fact, we really pulled a lot of stunts. Kudos to Maureen, who's sitting somewhere over there, for overcoming all sorts of obstacles, trying to put in an English-Arabic lexicon to improve the word alignment accuracy, but encountering morphological incompatibilities with the way the tokenization was done and implementing workarounds and so forth. So, yeah.
Actually, with hand alignments, you might find that your coverage, ITG coverage is even more, right?
Yeah, quite possible, quite possible. That's one of the next steps that we want to
Did
do.
you say, Kishore, say it again?
If you had hand alignments,
Yes.
I mean, these are noisy already.
Right. Yes,
These
yeah.
are- I mean, I'm saying ITG might, you might be able to show that ITG coverage is even more than what we have on the slide.
Yeah, the Arabic team in particular knows that I've been hounding them to find out if we have any already hand-aligned parallel corpora, even small ones that we can touch.
We have, and we should talk about.
Thank you.
So,
Excellent.
So
Uh,
the trees now are completely free here, right?
Yeah.
In other words, so as the trees can be selected and to optimize.
Yeah.
Why are there different results from English to Arabic than Arabic to English? Right?
We don't know. I mean, you'll see in a moment that that's quite typical of these experiments when I show you the other languages. If you just give me 1 second.
I don't understand what sentence.
Fertility of...
So given a geyser alignment in that direction.
Yeah, that's right.
Because in terms of what you're doing, it's a direction.
That's right. Yeah.
So I understand, going back, there's a Giza alignment, which is the optimal alignment Giza is trained to give you.
Right.
And you are seeing whether that alignment can be obtained by the ITG hypothesis.
Right.
And the answer is, well,
The-
isn't that alignment a sentence level alignment?
Okay.
In other words, I don't know what
Yeah.
word level.
So yeah, exactly. Okay. So let me explain. So in both cases, the computer does exactly the same thing, which is that it considers one sentence pair at a time and it byparses that one sentence.
Yes.
Okay. But then there's two ways of counting, right? It's kind of like word level error rates and sentence level error rates, right?
I see. I see.
Right.
So the question is whether the whole sentence can be covered.
Exactly. Every
The other line
100%
is-
alignment coverage in the
other line
sentence
what the
is
best-
required for
What is
this.
the best the
Yeah.
ITG can do, and then you count how many
Right,
words.
right. And we think both measures are interesting and informative because, you know, if you're looking at sort of the semantics of the translation, you might miss a couple of words and still have a, you know, fairly useful translation, right? So it's good to know this number. And this was something Zenz and I didn't report, and we're reporting about.
But Kishore's point really is that these alignments are noisy, so it's possible that the ones that you're actually
Precisely.
not getting are ones that just have
Precisely.
wrong alignment.
Yeah, precisely. Yeah, yeah. Yeah, we really want to run that experiment if we can get the hand-aligned corpus next.
Is it also possible to find out what fraction can be aligned with trees that look syntactically reasonable?
That's much more of a subjective judgment. And
thing just run a parser and then constrain the tree to be the English tree or a binary branch.
you guys are asking great questions. Yeah, we've just got the data to do that.
Yeah.
Yeah, exactly. Okay, so this is what the same results over here, but I've now put it next to Zenz and Nai's results for German and French. This was for mobile corpus. This was Canadian Hansards. And what you can see here, interesting trends, right? It compares consistently, first of all. So it did best on the German in their case. I don't know whether that's because of the nationality of their group. And then next best on French. And then, Arabic is doing worse than French, but not, I mean, it's by 5 points, say, right? And if you had to bet before I showed you this result, that's probably what you would have bet. I mean, here you've got Indo-European languages about as close as you're going to get. And now you're jumping to a completely unrelated Semitic language. 5 points is a reasonable drop. It's actually fairly consistent with what we saw in Chinese also. So, so I apologize. I haven't slept for 2 nights, and I ran out of time to go look up our results. But it's in this range. It's in this range. But modulo the next point I'm going to make. Sorry, 2 points from now. Okay. So the next point is that one of the key factors that you can tell immediately from that is already the morphological complexity. I mean, Mona's already doing all sorts of stunts to get around this, but nevertheless, there's a lot more to deal with, and so that's going to definitely hit us, and we can improve there. And yeah.
Just a quick thing. I'm not sure what an IBM constraint is really. So, is it the many to one? Yeah. So this is detailed in their paper. So this was the no.
IBM actually had a specific method for restricting the time, based on the time to search the space, which would otherwise be very large. So, and the exact details are in the paper. And basically, it was controlled so that they both had about the same amount of computation time.
Just a quick question. Do you have any estimation how many, like on average, how many walk-ins will actually apply?
Oh, how many inversions?
Inversions.
That's a good question. We'll find out. Okay, so now to that point. So what Zenz and Nye did, they didn't actually stop here. This inspired them to go do the error analysis. And what they noticed is a huge percentage of what they weren't covering, the remainder here, was being caused by very simple split lexical transductions. In particular for French, ne pas, ne rien, ne jamais, ne plus, right? And so just by putting a handful of those into the lexicon, which you can do without going outside of ITG expressiveness, then you get this massive jump. Right, you basically, especially on the French case, you're jumping like 15 points on the coverage because those things happen so often. And for both languages, they end up way up here. Right, and so this really begs, so we've talked about 2 of the next experiments we want to run. This is the 3rd one we want to run. It's like, okay, what goes in here? This takes error analysis and going back to my very, very first point, an Arabic speaker.
In some sense, you have such a construction in Arabic, right? Already.
Yeah.
But your numbers are already high.
Over here, you mean?
Yeah. Because in Arabic, you could say the French minister or something, and the minister are really coming from one word, just, right? So can you agree with that? Can you say it again? So, for example, the French minister and maybe foreign minister, the and the minister really come from one Arabic word, right? The definitive.
It depends how you do the splitting.
Yeah. Right, but human alignments, we tend to say that there is a split here. For example, our alignments do that. And that's why I'm surprised that the numbers are already high for Arabic, even without you using them.
Well, yeah. So it might be simply because we are already accounting for if they're right next to each other and not split. Right, and that might be a high percentage of the cases. Sometimes they split, and we're not getting those yet.
And since they're not requiring this to respect linguistic structure, you can do that flip. So they're tokenizing. I'm assuming they're tokenizing.
Or maybe they're tokenizing. Yeah, you may be right. Maybe they're splitting the out.
No, they're not.
You don't.
They're using,
okay, you're not.
You're not tokenizing.
Yeah.
And what about the SVO versus VSO issue? And that really serves the obvious challenge to ITG here, because if you assume standard phrase structure, you cannot transform SVO into VSO in ITG.
Okay, I don't have it in this short presentation, but if you remember the slide from that talk we had midway through the workshop where I showed this way of conceiving a complex transduction involving 3 or 4 as a composition of several small ones. So the linguistically meaningful chunk is the outside part, not what it's composed of inside. We can pull out the picture afterwards. Yeah. So, okay, just to summarize here, what we've got for this key question is the sort of first results for Arabic. They're indicating already high coverage within ITG expressiveness, certainly at the word level. And if we had to bet, I mean, obviously you want to run the experiment before you conclude, but if you had to bet, you'd guess that doing the split lexical transductions would probably get you here pretty well. So, this sort of tends to support the modeling assumption that we're making on our baseline models, as well as other people who are doing similar models. Yes, Arabic might well benefit from the efficiency gains that we can get if we impose the ITG constraint. And hopefully, even the traditional transfer-based types of architectures or EBMT types of architectures may look at this and realize that they don't actually have to resort, after all, to the SDTG level of expressiveness if they just sort of restrict their transaction rules to ITG expressiveness. Okay.
Just a few closing remarks. So take home messages from our work. Multi-parsing can be fast. This whole n to the 6th complexity that we keep hearing about is just the size of the search space. And our typical models are not too large for typical machines. Right? If we are not searching the whole space, we don't need terabytes of data just to parse a single, of memory just to parse a single sentence. Right? Our machines had, I think, actually quite a bit of memory, 4 gigabytes, but we didn't come anywhere near exhausting memory on most of the sentences that we were processing. Oh, and by the way, if I'm not mistaken, we didn't actually filter out long sentences. And on the Europarl corpus, some of those sentences are, what, hundreds of words? Yeah. This did not present a problem. I think, well, I believe that our first cut system is comparable in accuracy to an off-the-shelf FSD-based SMT system. Although, no statistical significance measures, only a small corpus.
It's based on what data?
This was on Arabic English news.
Which you...
This was the...
Maybe I was out and got a phone call, but I don't remember.
Based on this 10,000 word.
Yeah, this was in Marcus's presentation. Right. So, of course we have to run more tests to get more comparable, more strictly comparable results, but this gives me cause for optimism. And I think our student proposers showed, and I've also showed, that there's much low-hanging fruit to be had and to be picked to improve the speed and accuracy. This is just the beginning. I also want to conjecture that based on the nature of the algorithms that we're using, all this stuff is highly parallelizable. And so it seems feasible to do processing of typical size bitext with no more difficulty than people have with finite state-based approaches to SMT. In other words, we expect this approach to participate in the MT-eval exercises more and more frequently. So in addition to the take-home messages, we have some take-home software. It's on our team's webpage as I speak. You can get it right now. We have the MTV multi-tree viewer, which, by the way, does not require you to like or use our grammar formalism, as long as you can get a multi-tree into the file format that we use. However way you want to do that, the tool will display it for you in many ways. And of course, we have the GenPar toolkit. This will be an ongoing project. This workshop was extremely useful for jump-starting the effort, but we expect it to flower and bloom from here, hopefully attracting more developers than we have now even. There's right now a GenPar Announce mailing list that you can sign on to if you want to be kept informed of new releases. And there's also a developers mailing list if you really want to go that way. Here's some near future directions that some team members have suggested that they want to pursue. In addition to the two proposals that you've heard in detail, of course. We want to continue to work on phrases. We want to try other grammar formalisms and make transduction grammars out of them. Of course, we want to do more sophisticated machine learning and more sophisticated everything that they do in the monolingual parsing world. Because to us, translation is just parsing. Every advance that happens in parsing, we can directly apply to our work. So these are some of the motivations that I put up in the beginning, and now I can review and say, what have we done to further these aims? I hope, and I strongly believe, that the GenPar toolkit will lower the entry barriers to the field for new researchers. I think we've demonstrated the feasibility of this approach overall. This we have done in the short term. We have begun to answer some scientific questions that revolve around this approach to translation and translational equivalence. At least one of our undergrads has expressed an interest in going to graduate school, so we consider that an achievement. In the very near future, we hope to see accelerated progress in MT research, at least partially due to our work. And I want to say a little bit about, again, trying to reunite machine translation with NLP. In the late 90s, it seemed like machine translation was devolving into its own subfield, which paid a lot more attention to the speech and machine learning literature than to NLP. And of course, that literature is important, but I think NLP and machine translation can benefit each other because MT can improve by using the insights from NLP, particularly parsing, and parsing can claim another application if it pays attention to MT. To me, that's a good thing long term. So I just want to leave you with one thought as we look forward. The first SMT idea came around in '98, and the first publicly available toolkit was created here at Johns Hopkins in '99, 11 years later. And this approach became dominant in the field about 3 years after that, I'd say roughly around 2002. SMT by parsing was first proposed in 1995. 10 years later, now in 2005, we have the first publicly available toolkit for doing that, and I'll leave you to draw your own hypotheses about what happens next.
Are you done?
That's it.
I'd like to open the floor to all sorts of questions, but maybe you want to ask first the questions of him, and then I'd like to see if anybody wants to make any remarks or anything about the workshop as a whole or the various three groups. So, any comments?
So I think your comment that parsing techniques or graded deduction techniques can generally help MT or anything else you want to do in that framework. In that vein, it seems reasonable to ask when you use your system as a monolingual parser, how it compares in speed and accuracy to the state-of-the-art monolingual parsers at the moment. I mean, obviously you could soup it up and put all the other stuff in.
Right. So it is an interesting question. I agree. I couldn't begin to form an answer. We just haven't tried that at all. Been focusing so hard on that chart. So yeah, I mean, in fact, the modularity and abstractions in our toolkit may be of interest to people working on monolingual parsing as well. In principle, there's no reason why it can't just be used for monolingual parsing if people want to do that. So it's yet another downloadable parser for monolingual applications also.
So you have the parser plugged in at various places in your big chart, and the same general algorithm is being applied in each of these cases. Are you losing any special case efficiencies in any of those individual usages? And how do you plug in, say, I know I can make certain assumptions over here in my chart that would make it more efficient or more effective? How do you plug in these sorts of special case efficiencies?
Right. Should you answer that, or should I take it?
Yeah, I can answer that. So I think the answer is you can use different parsing algorithms for the different components. So if you wanted to use, for example, the CKY implementation, we've got translation, but then the agenda-based parser for alignment, you can do that. So I think it's quite flexible in terms of what algorithms and data structures you want to use.
You just have the subclass. If you're interested in making a chart that's more optimized, right? You just subclass the chart and make sure you have the same interface, and then plug it in the part that you want in.
Right. And the design allows what is essentially an easy override of the agenda as a whole.
Say we have a new language pair, and we somehow manage to get a parallel data. What's the minimal requirement to run SMT by parsing using the toolkit?
Yeah. So the toolkit comes with these things we call sandboxes, right, which are an encapsulation of the entire system. We have these for 3 different language pairs. If you have a new language pair, if I had a new language pair, if I wanted to work with, right, what I would do is download the toolkit, unpack it, do a recursive copy of whichever of these sandboxes is the closest in terms of language pair or available resources to what you're doing. Just do a recursive copy into a new place, right? Copy your data into the input subdirectory. There's actually a subdirectory called input. Right? If you want to, well, you probably should
substitute, for example, if you want to use a monolingual parser to bias trees on one side, there's a way to plug that in. You'd have to make sure that the format of the output is the same, but we use basically pen tree bank tree format, so that's fairly standard. What else did you have to do? There's sort of an infinite amount of stuff you could do, right? Because for every language pair, you can plug in so many different resources, whatever you have. But the minimum, I think, is pretty much nothing. Just copy into the input, and well, you probably need to tokenize it, right? But I think that's it.
Enough to jumpstart the system.
Yeah. I think. I mean, can other team members think of, like, for arbitrary language pair, what is the minimum that you would have to do other than just copying the sandbox to a new instantiation? Nothing really.
Tokenizer and word-to-word model.
Word-to-word. Okay, but even word-to-word model, if you've got tokenization, you can just run Giza, right? I mean, it may not be very good, but
You'd have to do that somewhere. But we have that sort of plugged in, right?
yeah, that's right. So in fact, I think we're redistributing Giza as part of our toolkit as well, if I'm not mistaken, right? Because it's open source and GPL, so it's all just in there, plugged in already.
So just a suggestion, one of the things that makes HTK a very useful tool in the field is the fact that there are a couple recipes that are examples of how to sort of set up the models and get them going. So a recipe, say, in English-French, might actually be a very nice thing.
But that's what the sandboxes do.
But no, you have a recipe, you do the whole setup for a language pair, and that's released with the tool.
Yeah, that's what we have.
But he's saying if you wanted to set up a new one, so the steps that you'd have to go through.
The recipe is,
Just giving people an integrated system for English-French is very different than you have to go through these kinds of steps in this way.
right. Okay, so as I mentioned, for a specific language pair, you could do all kinds of things. But the minimum thing that you have to do is two things. Recursive copy of a sandbox, plug new data into the input directory. That's it. That is the recipe.
Okay.
I have a question actually to the guy. So if I may draw a kind of conclusion from your talk about ITG, I go back to the parsing literature, and then I see a lot of people use context-free grammars to build a space of parses, and then disambiguate on top of that. So is that the same ITG?
Yeah, I think it's a good analogy. So I made that point about the fact that the notion of context-free sort of shadows into much finer grained classes when you go to transaction grammars. And I think one of the things I'm trying to get across is that people historically, for the last several decades or more, have sort of just intuitively leapt to the assumption that the natural analog of context-free at the bilingual level should be the syntax-directed transaction grammars, because the production rules look like they look superficially similar, but not realizing that it's exponential at the bilingual level, unlike the monolingual level. So part of what I'm trying to say here is the more natural, or the more close analogy to the monolingual case is ITGs, where you do have the two normal forms, where you do have the polynomial time algorithms that are quite efficient in practice. And so
that's just one opening of my question. That is, where does the statistical part of ITG kick in? Because that is like probabilistic context-free grammar. They have to be enriched in many ways to use them for disambiguation. So I'm wondering about the same thing for ITGs.
So the area of how to parameterize your ITG is there's a lot of stuff that's happening. You saw the lexicalized ITGs that Zhang and Gildea proposed, for example. Vilar and Vidal have been working with yet an alternative probabilization of ITGs. And there's actually quite a few, and then the various headed formulations and combinations of headed and lexicalized formulations, the Kang Ling and Colin Cherry, for example, are all alternative probabilizations of this. And you have to go through, I think, much of the same kind of experimentation and analysis that we've seen in the monolingual world.
Okay, one loosely related question, I could jump in. When you allow the bilaterals to split the nasal, in the French case, you need to get more coverage. Where does your expressiveness go up in the coverage? Or does it stay at ITG?
It stays at ITG, yeah. Because we're talking about lexical transactions. So it's very, I can draw you the picture very easily. Yeah.
Okay. One more question.
Okay. So this is partly to see what you guys did, and also partly sort of advice if we were to use your toolkit how to do this. So you could basically, for a new language pair or for an existing language pair, basically start with existing alignments, word alignments, and then use your toolkit to induce, to train grammar, right? Or you could use a monolingual parser and try and do the alignment step using this approach as a starting point. Which way works better with sort of the technology the way that you have it right now, and what would you recommend doing for someone that's starting at the point that you are right now?
Well, it depends, right, on many things. First of all, it depends on why you're doing it. If you want to do it for educational purposes, of course, I'd recommend starting with as few constraints as possible to see what happens. If you're doing it to get the best possible MT system, then I have no idea. We haven't done those experiments. I think it'll really depend on particularly what data you have and basically whether this bias that you get from monolingual trees or word alignments is a good bias, right? I mean, if I had a really, really good parser, and by the way, when I say good, I don't mean good in the linguistic sense. I mean good for the purpose of translation. If I had a good parser for that purpose, then sure, use it, right? If I had a parser that produces garbage trees that aren't good to anyone, then I wouldn't use it, right? It's really an empirical question that we have to investigate.
Okay, thank you. So I don't know if anybody would like to make any remarks or any questions to the other teams or general remarks about the workshop.
Very interesting work. Very nice.
Okay. Anybody wants? Laura, do you want to say something about what they ought to do before they leave?
Any of the students who made presentations yesterday and today for the post-workshop awards should stay somewhere nearby in case the judges want to talk to you, preferably in the lab. That would be the easiest place to find you. If you need to go and grab lunch, at least let me know which direction you're headed so I can find you upstairs. I sent a couple of emails about just cleaning up the lab, computer files and stuff, so the lab is open, available for the afternoon, evening. We'll hopefully see all of you tonight at 7 o'clock at Jason.
And we're serving lunch tomorrow?
Tomorrow, yep.
I know it'll be a soccer game afterwards.
After
The game translation team versus everyone else.
Tomorrow or
Tomorrow afternoon after lunch.
tomorrow afternoon?
Come prepared.
Any other remarks or news? Okay, well, thank you very much for your hard work and.